So, yeah. So today we will uh, continue our studies in AC circuits, but we will take a slightly different topic, which is called three-phase AC circuits. It's not different from what we have studied. It's a special case, you can say. Okay. Yeah. So how an AC voltage is generated in a generator. Let us start from that. Roughly speaking, so in this diagram, you can see that we have a two-pole magnet, north pole and south pole, which is mounted on a shaft, and the shaft can rotate. Okay, and suppose this magnet is rotating inside a cylindrical space. Okay, and these blue lines show the flux lines, magnetic flux lines emanating from the north pole, and they are continuous, so they will travel in a closed path and then they will enter through the south pole. And here we are only showing portions of these flux lines, magnetic flux lines. Okay, and this entire arrangement is rotating in a cylindrical volume. Now, imagine what happens if I have, say, a conductor which is shown here in red color. Okay, suppose this conductor is placed like this here. Okay, so this is outside the rotating magnet. Okay, so this side is actually behind this scene, which we cannot see. Okay, and now these flux lines are cutting through the two sides, both the sides of this conductor. Okay, maybe copper or something, some conductor. Now what will happen? According to Faraday's law, some EMF or voltage will be induced on the two sides, in the two sides of this conductor. And using Fleming's right-hand rule, you can find out the direction of the EMF in this conductor. Okay, this conductor is, this magnet is rotating anti-clockwise as seen from the front. That means this conductor is rotating with respect to the magnet in clockwise direction, and if you apply right-hand rule, Fleming's right-hand rule, you will get the polarity of the induced EMF. So in the induced EMF in this case will be in this, so it will try to drive a current in this direction on this side of the conductor and here in this direction. So therefore I can say that this side will be positive compared to this side, and this side will be positive compared to this side. Okay, so overall here we will get a positive polarity, here we will get a negative polarity induced. Okay, let me call this conductor as A prime. So side A, terminal A is positive, terminal A prime is negative. And then this magnet is rotating periodically. I mean, so after a while the south pole will come in place of north pole, and then the polarity of the induced voltage will also change. Therefore the induced voltage will also be periodic in nature. It will oscillate between positive and negative, and it may vary like this. Okay, whether it will be sinusoidal or some other pattern, that depends on many other factors that we will not consider here. We will just assume it to be sinusoidal for now, and how to make it sinusoidal in an actual generator, that we are not discussing. But anyway, we are sure that this voltage is going to be periodic in nature, sometimes positive, sometimes negative, depending on whether the north pole is under the side A or the south pole is under side A, like that. Okay. Now
So,
consider, yes.
sir, I didn't understand properly. Could you please just explain again? Sorry, sir, I didn't understand properly.
Okay, so consider the moment when this north pole is passing just under this side A, okay, the upper side of this conductor. Okay, then what will happen? So some EMF will be induced, and how to find the direction of the EMF? So you all apply the right hand rule. I can't, I mean, you can't see my right hand on screen. So if you apply the right hand rule, your forefinger should be along the direction of these magnetic fields. Your thumb should be in the direction of the motion of the conductor with respect to the magnetic field, so which is in this direction. Okay, so the conductor is moving in this direction. Your forefinger should point along the flux. Okay, so basically the conductor is moving along the periphery of the cylinder. Okay, and in the radial direction we have the magnetic field flux lines, called that B. Okay, this is V velocity. Then perpendicular to that, that means along the height or length of the cylinder, we will have the EMF. And if you apply right hand rule, you will get the direction of EMF like this. Okay, so it will try to drive the current in this direction. And in the other side, which is below the north pole, okay, when this north pole comes directly below this side A prime, then here, sorry, south pole comes directly below this A prime, then the induced EMF will be in the opposite direction like this, because here we have north pole, here we have south pole. So overall, the current will try to flow in this path. Okay, and then there should be also some closed path outside for the current to flow. But nevertheless, whether the current is flowing or not, it is trying to drive this current in this direction. So that means this side will act as the positive end of a voltage source, this side negative end of the voltage source. Okay, and then after a while, this south pole will come in the place of north pole will go in the place of south pole, therefore the polarity of the induced EMF will also get reversed. Okay, then so if I call VA prime is the voltage of terminal A with respect to A prime, then that is sometimes positive, sometimes negative, like this. Okay, is that fine?
Yes, sir.
Okay. Achha. Then now let's see what happens if we have one more conductor. Okay, this yellow one. Let me put it like this. Okay, so you can guess that actually this will go behind the scene, behind these magnets, etc. And this you call it B, and B prime. Okay, so side B is in front, side B prime is behind. Now this conductor is also there surrounding the rotating magnet. What will happen to this conductor? Some voltage will again be induced in this conductor B prime, but will this voltage be exactly similar to the voltage A prime? Yes, no, or what will be the difference? Anyone?
Magnetic
I
same,
think
but the phase are
voltage
Due
will
to different field.
Right, absolutely right. So see, this conductor B prime is at a different point in space. Okay, so therefore there will be a phase difference between the voltage generated in A prime and between B prime. Okay, So suppose this angle is 120 degree in space. Then the moment when this north pole crosses below this side A, after some time from that, the north pole will go under the side B. Okay, therefore the induced voltage in this conductor BB prime will lag the voltage induced in A prime by 120 degree or by some time. Okay, so if this is 0 degree, this is 180 degree. So basically I am plotting omega t versus induced voltage, where omega is basically 2 pi times n, where n is the speed of rotation of this magnet, okay, in revolution per second. Okay, then this is 360 degree and so on. Now the voltage induced in BB prime will lag the voltage induced in AA prime by 120 degrees, so that will be somewhat like this. Okay, so this is the voltage VBB prime. Okay, and similarly now if I take one more conductor, this blue one, and let me put it here, okay, such that this angle from here to from here to here, okay, call this C and C prime. Okay, then the angle between B and C is again 120 degree. Okay, and so this side is actually behind this in. These are all behind this in. Okay, so now the voltage induced between C and C prime will again be 120 degree lagging the voltage BB prime. Okay, so that will be somewhat like this. Okay, so this is V, C, C prime. So in this way, we have three voltages induced. Okay, so if I call V A prime is equal to say some V P multiplied by sine omega t, then what will be VBB prime? That will be VP sine omega t minus 120 degree, and similarly VCC prime will be VP sine omega t minus 240 degree. Okay, same magnitude of voltages, all of them have same magnitude of voltage, but the phase angle is different. Okay, now this VCC prime you can also write in this way: omega t plus 120 degree, because we are just adding 360 degree. So adding 360 degree doesn't change anything. Okay, so yeah. So basically we have three voltages at 120 degree phase difference from each other. Okay, is that fine? Now Now in the generators, in generating stations, the generated voltages are always of this nature. We call it three-phase voltage. Okay, so basically we have three voltages, three-phase voltage. This is how the voltages are generated in generating station. So you can think that there are three voltages generated simultaneously, or you can think that practically there are 3 generators acting together, working together. Now, what we do is this.
Excuse me, sir,
Yes,
I
yes,
had a doubt.
yes.
Sir, so this isn't limited to three, right? We can use any number of conductors. Or
Yeah. So there are 2 things I will mention. Number 1, in principle, you can take any number of conductors and the angle between them can also change. Okay, so I have here taken 3 conductors and I have placed them 360 degree by 3, that means 120 degree apart from each other. But in principle, you can take, say, more conductors, maybe 4 number of conductors placed 90 degree apart. Okay, that is also possible. You can do that. And but 3 conductors 120 degree apart is the most common one. This is what we have in almost all generating stations, in all generators. Okay, and that is called 3-phase voltage. There are other possibilities also. We will talk about them when time comes. But this is the most common one. 3 conductors 120 degree apart. So 3 voltages 120 degree phase difference between them. That is one point. Another point I should mention is that here I am showing, consider just this red conductor. I am showing only one conductor or one turn, but practically, you know what we have, basically it continues here and then it basically it has many number of turns, okay, like this. Okay, so basically it can have many number of turns. Then what happens? Then in each turn some voltage is induced and the total voltage will get multiplied by the number of turns. So we will have higher amount of voltage. Okay, so if we have only one turn, the induced voltage will be very small. So therefore we have many turns, say n number of turns, so that the voltage induced between the 2 ends of the coil, n turn coil, is significantly larger. Okay, so that is another fact. Okay, acha.
yes,
Now when we have these 3 sources, okay, basically they are part of one single generator, but consider them to be 3 different sources, no problem. What do we do with this? So we will connect these 3 sources like this. Okay, so suppose this is terminal A and A prime, this is terminal, say, B and B prime, this is C and C prime, okay, of 3 generators or parts of one single generator. Now we can connect all the prime ends, A prime, B prime and C prime together, and unprime ends are left open, floating. Then we will take long transmission lines or conductors from the generating station like this. These are transmission lines, conductors, and then in the other end we can connect loads or impedances, like, say this is my house, say this is my friend's house, and maybe this is another friend's house, and they are also connected like this. Okay, so we can connect them in this way. Okay, let me call this, this is also A, B and C. These are some impedances. So this may be our houses, our factories, whatever. Okay, call these impedances as ZA, C and ZB. Okay, so this way the loads are connected in a power system. This is one possible way. This is called a star connection, because or we can also call it a Y connection, because the three sources are connected like an inverted Y. Okay. Similarly, this load side is also star connected. Okay, and now we can so normally this common point is normally grounded. Okay, we can also have another wire going from here to here. Okay, like this. Then this wire is called the neutral wire. Okay, N for neutral, and these three other wires are called phase wires. Okay, so let me call this phase A, then this is phase B, and this is phase C. This neutral wire may be present or it may not be present. Sometimes it is not there. Okay. Based on that, we have two types of systems. One is called four-wire system. So neutral is present, and we can also have three-wire system where neutral is absent. Okay, so this drawing is of a star connected three-phase four-wire system. Okay, three-phase four-wire star connected system. Achha. Now, also there is another possibility which is like this.
Sir, why did we ground one connection?
I will come to that later. Okay, so yeah, in fact, I mean, this end can also be grounded. This end can also be grounded. Okay, I mean, one problem, if you do not ground anything, then the voltages, absolute value of the voltages are undefined. Okay, and so all voltages will be floating. Then we can only define the relative voltages between 2 points, but absolute voltage is undefined. But when you connect any particular point to the ground, then that point is at zero potential with respect to ground, and all other points in the circuit will have precisely defined absolute potentials. Okay. Yeah. Now, one more thing I should mention, that suppose you ground both these star points, and then if you do not have this neutral line, then this is also practically same as four-wire system, because this ground or earth will act as the neutral line, even if there is no explicit neutral line. When you ground the two star points, then the earth will act as the neutral line. Okay? Yeah. Acha. Then there is another possibility which is as follows. So suppose I connect these three sources in this way. Okay, say suppose this is A prime, suppose this is B prime, this is C prime. Okay, then they're connected in a closed loop. Acha, now, yeah. Then, acha, if I just connect them in this way, acha, fine. Then we can take long transmission lines like this, and on the other end we can have loads like 1, then 2, 3, and here also you can connect them in this way. Okay, now suppose this is Z1, Z2 and Z3. Okay, this is called a delta connection. Okay, or we can write it like this, Greek alphabet delta, and so this side also is delta connected. Load side is also delta connected here. Okay, but it is not necessary that you have to have both sides connected in delta or both sides connected in star. You can also have one side connected in star, another side connected in delta. Okay, so that is also possible. So we may also have sources connected in star and loads connected in delta, or we may also have sources connected in delta and loads connected in star connection. That is also possible. Okay, acha. Now let me give you some terminologies. The voltage between any two lines, like these two lines, is called line to line voltage. Okay, so similarly from here to here, this is also line to line voltage. Okay, in this diagram also we can say that say from here to here, this is a line to line voltage. Let me just write VL, L for line to line voltage. Okay, and then the voltage between one line and the ground is called phase voltage. Okay, so this is a phase voltage. Also this is called phase voltage from here to here. Basically the voltage across one source or one load, that is called phase voltage. Okay, so this voltage from here to here, this is phase voltage. In this diagram also, so the voltage across this one source is phase voltage. Okay, so what we see in delta connection, phase voltage and line to line voltage, they are same. Okay, so even if you call, say, this voltage from here to here across this load, this is also phase voltage. So in delta connection, phase voltage and line voltages are same. Okay, so let me write for delta connection, phase voltage, I mean the magnitude of phase voltage is same as magnitude of line voltage or line to line voltage. Okay, this is for delta connection. However, this is not true for star connection. As we can see here, the phase voltage is from terminal A to A prime, that is different from line to line voltage, which is say from between A and B. Okay, so what is the relationship between phase voltage and line voltage for a star connection then? Okay, so let us see. So if we have, let me copy this part. Now, suppose if the phasor representation of voltage AA prime is VA bar plus minus, okay, and the phasor representation of VBB prime is VB plus this side minus this side, and here similarly VC plus minus. Okay, so basically here I mean VA corresponds to VA prime, which is say V peak sine omega t. Okay. Similarly, we have VBB prime, which is V peak sine omega t minus 120 degree. Okay, that will correspond to V phasor VB bar, and similarly VC. Now, if I draw a phasor diagram, okay, representing VA, VB and VC, how should that look like? Okay, so suppose this.
Sir,
yes,
I had one doubt.
yes, please.
Sir, for delta connection, phase voltage is defined for one line.
So for delta, see, phase voltage is the voltage say from B to B prime, that we can call phase voltage, or from A prime, that is also phase voltage. Basically, phase voltage is the voltage across one element, one source or one load. Okay. And in this case, it happens to be the same as the line to line voltage. Line to line voltage is between two transmission lines. Okay, so they are
Yes,
same.
sir.
So here the phase voltages and line voltages, they are same.
Yes, sir.
But for star connection, that is not the case. Acha. Now, for star connection, suppose this line represents VA bar. Then how should I represent VB bar? That should be here 120 degree apart, VB bar. This is 120 degree, magnitude or length should be same, and VC will be further here. This is also 120 degree. Okay, and now suppose the phase voltage okay, so I let me not use P here, call it V naught, because I was using P to mean the peak value, but I also have to use the letter P, alphabet P, to mean the phase voltage. So let me change my notation. Okay, Achha. So now suppose Vp is the magnitude of phase voltage. That means this length corresponds to Vp. This length also corresponds to Vp. Similarly, this length is also Vp. Now we have 3 transmission lines. How much is the voltage from here to here? Call that VAB bar, phasor voltage. That is basically I have also should put a reference direction like this, plus minus. Okay. Now how much is VAB?
VA minus VB.
Absolutely right, VA minus VB. Okay, so in this phasor diagram, let us find that. So VA minus VB, so that will be this line pointing from B to A. So this is VAB bar. How much is the length of VAB bar? Using trigonometry, you can find it out. How much is that? How much is this angle? This angle?
30 degrees.
30 degree.
30
Absolutely
degree.
right.
30
So if
degrees.
this is 30 degree, let me put a bisector here. Okay. Then how much is this length?
3
V-
by 2.
VP plus 30.
Vp cos 30. So then how much is this total length? That will be
V naught root 3.
2, absolutely right.
2 VP cos.
cos 30, so which is same as Vp into root 3. Okay, so let me call this VL, line to line voltage. Okay, so what do we see here? That VL is root 3 times Vp. VL is the line to line voltage and Vp is the phase voltage. I mean the magnitude of the phase voltage and magnitude of line voltage, or basically the RMS values. They are related by line to line voltage is root 3 times the phase voltage. And what is the phase angle relationship between VAB? So what will be the phase angle of VAB? So angle of VAB is how much in this diagram? 30 degree. Absolutely right.
80.
Okay. Acha. Now, there are 2 possibilities. One possibility is that, as we have seen here, here we see that VA leads VB by 120 degree and VB leads VC by further 120 degree. This is called ABC sequence. Okay, A comes first, then B, and then C. Similarly, it is possible that in some source we have, basically, in this diagram only, if I just call this as C and this as B, then what happens? A comes first, then C, then B. Okay, just I'm changing the names. Okay, so then how will the phasor diagram look like? So if this is VA, then comes VC, and then comes, then comes finally VB. Okay, so now what is the phase sequence here? This is called ACB sequence. A followed by C followed by B. Okay, once again, here also you can calculate the line to line voltages. For example, this line, this line represents what? Voltage V AB.
ABC.
Okay, this is again root 3 times the voltage VA or VB. Okay, similarly, this voltage what does it represent? V, BC or CB? BC, according to our convention. Okay, acha. So we can have two types of phase sequences. Now the important thing that we have seen, that for star connection, this is for star connection, for Y connection, line to line voltage is √3 times the phase voltage. And for delta connection, they are same. Line to line and phase voltages are same. Okay, so far?
Yes.
Achha. Next.
Sir, in the star connection, what was the angle VAB? What does it signify?
Which angle?
The VAB equal to 30 degree.
Yeah. I mean, what I mean is that if you write the phasor value of VAB, okay, so something like VAB magnitude with the angle, what will be that angle? That will be 30 degree when we considered the angle of VA to be 0. Right?
Oh, okay.
Okay, so that's what I meant. Okay, fine. Achha. Next, achha. Now, let me go back. This is a star connection, both sides star. Now, the current that flows through these transmission lines, these are called line currents. Okay, so this is also a line current. I mean, the value of this current is called the line current. And the current that flows through, say, one particular load, okay, say this current here, this is called a phase current. Okay, similarly, this is also a phase current. Here also I can say this towards this load side, source side, this is also a phase current. Okay, now what is the relationship between phase current values and line current values for star connection? We see they are same. Okay, so basically they are same. So phase currents are same as the line currents for star connection. Now let's come to the delta connection. Okay, so here again the current that flows here or here or here, they are the line currents. Okay, this is also a line current. However, the current that flows say here, that is called a phase current. Okay, this is also a phase current. Okay, similarly here also this you can call a phase current. Are the line currents and phase currents same? No, now they are not same. Okay, so let us find out what is the relation between line current and phase current in this case. But before that, yes, please.
Sir, in this case, does the line current, phase current in both the part, like left and right, will be same?
Not necessarily. Under particular assumptions, it will be same, but not necessarily always. We'll come to that. Acha, so what I was saying, now, if so there are two possibilities. Okay, let me make some space. and right here. Okay, so suppose when the voltages VA, VB and VC, they are all equal, okay, and the three voltages are 120 degree apart. And if these three loads, Z1, they are complex loads, complex value loads, so Z1, Z2 and Z3, if they are also equal, okay, then we call it a symmetric, this is a symmetric situation, we call it a balanced system. Okay. If the source voltages are equal and 120 degree apart, then we will call that a balanced source. However, the loads, three loads may not be equal, then the load will be called unbalanced. Okay, and if the three loads are equal, we will call the loads also balanced. And if both the sources and loads, they are equal, and sources also need to be 120 degree apart, then we will call it a completely balanced system. We may have only balanced source but unbalanced load, and we may have everything also balanced. Okay, so a very special case is this, a balanced system when all source voltages are equal and 120 degree apart and loads are equal. That is called balanced system. Okay, that is also true for star connection. Okay, so also for star connection, if ZA, ZB and ZC, they are complex value impedances, if they are equal, and if the source voltages are also equal and 120 degree apart, we will call that a balanced system. Okay, fine, otherwise unbalanced. Now, consider so we consider a balanced, say, delta connected system. Okay, so let me consider the load side. You may also consider the source side. Suppose this is, let me call this phase A, B and C. Okay, so this is basically A, B, C. Now, suppose the supply is a balanced supply. Okay, so I'm just drawing a block diagram. So here we have a balanced supply. That means voltages are 120 degree apart and of equal magnitude. Okay, and then suppose this is, say, call it Z1, Z2 and Z3. Suppose they are also equal, all are equal to Z. Okay, so let me just write Z. Okay, then since this system is completely symmetric, you can readily guess what will happen to these three currents. If I call it IAB, this is IBC, and say this is ICA, what can we say about okay, and say this is VAB from here to here, plus minus. Then how much is IAB? This is
AB by Z.
Absolutely right. So similarly, you can find I, BC and ICA. Okay, so what can we say about these three currents, IAB, IBC and ICA? How about their magnitudes or RMS values? They will be same. Equal, absolutely. And what about the phase angles of IAB, BC and CA? They will be 120 degree apart.
21.
Yeah, because VAB, so suppose this is like this, some value V angle 0 degree by Z, then we have I BC, that will be V BC by Z, which will be V angle say minus 120 degree by Z, and similarly ICA you can find. So we see they are also of equal magnitude but 120 degree apart. If so, now if I call this current as IA, how much is IA? How to find that? We can draw a phasor diagram. Okay, suppose this is IAB, then IBC may be here, and ICA may be here. How much is IA?
IAB minus ICA.
IAB minus ICA. Just apply Kirchhoff's law, KCL at node A. So that is IAB minus ICA. So AB minus CA. So that will be this line. This is IA. Okay, now from this, can you tell me how much is the magnitude or RMS value of IA in terms of the magnitude of IAB?
Root 3 times.
Absolutely right.
Root
Because
3 times.
this is the same geometry as we have seen here. Okay. So that will be root 3 times the magnitude of IAB. Okay, or IBC or ICA. So essentially here I will write the line current IL, L for line current, that means the current that flows through these transmission lines. So that is root 3 times the phase currents, which are the currents that flows through these individual nodes. Okay, this is for delta connection. And what is the relationship between line current and phase current for star connection? They are the same. Yes.
Equal.
Yeah, equal. Okay. Fine. Acha. Now, so we talked about two possibilities. One is a balanced system. Another is an unbalanced system. Now, when the system is balanced, this is a special case and is most easiest case. Why easiest? Because to solve the circuits with balanced system, we can just exploit the symmetry of the circuits. 3 voltages identical, 3 loads identical. So utilizing the symmetry, we can solve these problems very easily. However, unbalanced system is not difficult, because unbalanced system you can treat as, okay, any AC circuit with 3 sources, their values may not be equal, so what? We have 3 sources, 3 loads, values may not be equal. Since we can solve any circuit problem, so using general circuit solution methods, mesh methods, loop methods, whatever you like, nodal methods, you can solve it. That's not difficult. But balance system is excessively easy, especially easy. Okay, so therefore we will talk about balance systems a bit more and how we can solve them more easily. However, please don't think that unbalanced systems are not in syllabus or so. It's not that. That's a general system, of course. Acha. Next, we will talk about the power in three-phase circuits. Okay. So let's consider the balanced situation first, because unbalanced situation is a general situation where we cannot utilize the symmetry. Achha. Now, suppose we have a star connected system. Okay, suppose this is A, B, C plus minus sinusoidal. Okay, so this is ZA, ZB, ZC, and they are equal. Okay, suppose ZA is equal, so this is equal to Z angle theta. Okay, so all of them are Z angle theta. Now, call this voltage VA, okay, from here to here, and call this current as IA. How much power is going from the source side to the load side? Anyone?
VA.
Yes, right. So power, total three-phase power is how much? How much power is consumed by this ZA alone?
VA
V magnitude of VA, magnitude of IA, and
cos theta.
cosine of theta. Okay, now any question? Okay, so now this is the power consumed by ZA. How much will be the power consumed by ZB and ZC? Since it is completely symmetric, you can easily guess that ZB and ZC are also consuming same amount of powers. So I just multiply this by 3. Okay. So essentially what do I get? I get 3 times this magnitude of VA is nothing but phase voltage. Okay. Call it VP. VP is the phase voltage. IA is, magnitude of IA is IP multiplied by cos theta. Okay. So here I mean VP is the phase voltage and IP is the phase current. Now we will write this as √3 times VL IL cos theta. Why can we do that? Because IP is equal to IL, that is the line current, and VL is √3 times VP in this case. Okay, that is the line voltage, line to line voltage. So we can write it in this way, root 3 times VLIL cos theta. Agreed?
Yes.
You could also write it as 3 times VPIP cos theta. That is also correct. But why I am writing as in terms of VLIL, we shall see soon. Okay, so, but this is, we have proved considering the star connection. Now let's see what happens if we have a delta connection. You have to put it in a circular way. So minus plus minus plus minus plus like that. Now again, suppose this is z angle theta. This is also z angle theta, balanced. This is also z angle theta. And source is also balanced. Call it A, B and C. How much is the power going from source to load? Total power. Okay, suppose this is VAB. Okay, then how much is the total power? Before that, how much is the power consumed by this, call it, consider this load. How much is the power consumed by this circuit load? Total, by this one alone. How much is that? Okay, so for that, I also have to write the current, call this current as IAB, phasor. Okay, how much is the power consumed by this load alone? That will be VAB magnitude, IAB magnitude, and cosine, the angle between VAB and IAB. But how much is that? Theta, because load angle is theta. Okay, cos theta. So this is the power consumed by one load of these three phases. So total power will be 3 times because it is completely symmetric. Okay, so now this VAB is nothing but VL, and IAB is what? This is phase current or line current. Okay, let me first write this as VAB is also phase voltage. Okay, then IAB is phase current cos theta. But now phase voltage and line voltage, they are same. So in place of VP I can write VL. But what about IP? IP is 1 by root 3 times IL. Okay, so I write root 3 here and IL here. So once again we see this formula is true even for delta connection, root 3 VL IL cos theta. Okay, so this is true for both star and delta connection. Okay, fine. Acha. Now, any questions so far? Anyone? No? Excellent. Okay, so next we shall talk about power measurement. Three-phase power measurement. Acha, before that, one more thing I have to state. Okay, just let me copy this. Now here, suppose this is balanced. So all these loads are identical, call them Z, Z and Z. Okay, now, and these voltages are also 120 degree apart and of equal magnitude. Question. Acha, if I call this IA, let me call it IA, then this is IB and IC. These are line currents. In this case, they are also same as the phase currents. And this voltage is VA. This voltage is, plus minus like this. Here VB minus plus, and VC is from here to here, plus minus. So what do we have? VA, VB, VC are of equal magnitude and 120 degree apart. Okay, so if I write VA equal to V angle 0 degree, then VB will be V angle minus 120 degree and VC will be V angle plus 120 degree or minus 240 degree, same. Now the question is, find out the value of IA, IB and IC and also this current IN. How much is IN? We have a perfectly balanced system. Okay? I will wait for a minute for you to find out the value of IN. Before that, how much is IA? What can we write? IA is this current here, which is also flowing here through ZA or Z. Okay, how much is IA?
VA by Z.
V angle 0 degree
by
by
Z. Okay, how much is IB? VB by Z. How much is IC?
VC by
by
Z.
Z. Okay, so how much is IN?
Sir, IN will be 0.
IN will be 0, but before that, if you consider this star point in this load side, okay, if we apply Kirchhoff's current law, what can we write? IN is IA plus IB plus IC. So we have to add these three currents. Now if we draw a phasor diagram, okay, so yes, yes. Okay, so suppose these are the three voltages, VA, VB and VC. Okay, and then how will be the current IA? IA may be somewhere here. That is VA by Z. Okay, so if Z has an angle theta, so then this angle will be theta. Similarly, IB will be here. This angle will be theta, and IC will be here. This angle will be again theta. So we have three vectors or phasors of equal magnitude and 120 degree apart. What happens when you add them? They are symmetric. They are symmetric, 120 degree apart. Add three vectors. What will be the resultant? Resultant will be 0. Right? From your high school physics, the resultant will be 0. So if so, one advantage of this three-phase system is that if we have a balanced load, then there is no neutral current. Therefore, we can omit this neutral line. We need not have this neutral line because there is no neutral current. Okay, so even if we do not put the neutral line, there is no harm. So then, therefore, essentially, what you see, we have only 3 lines, effectively only 3 lines. Okay, only 3 lines are there to carry power or current from the generating station to the load side. But if we had 3 separate generators generating these voltages separately, then how many conductors do we need to carry the same amount of current and same amount of power? If we had this separately, we need 3 into 2, 6 conductors, 6 lines to carry same current if we have 3 separate generators. But when we have a 3-phase generator working together, then only 3 lines are enough. So the cost and required of amount of conductor copper is reduced to a much significant amount. Also, one more thing, let me just finish. One more thing. Now, suppose it is not necessary that the load will be always balanced. Okay, suppose the load is slightly unbalanced. Okay, suppose ZA, ZB, ZC, they are slightly unequal, then there will be a small amount of neutral current, and you can practically put a very thin amount of conductor. Okay, so you can put a very thin amount of conductor compared to the thickness of the other 3 conductors which are carrying these line currents IA, IB, IC. Compared to that, the neutral line may be much thinner. And even if you put the neutral line, only 4 lines are enough compared to the 6 lines required for 3 separate supplies. So that is one advantage of 3-phase system. Okay, so let me just mention it so that you remember. So one advantage of 3-phase system is conductors required for transmission line is less. For transmission line, is less, lesser than 3 separate single phase systems. Okay, any questions so far?
Sir,
Yes.
if the system would not be unbalanced or would be unbalanced, in that case, is it necessary to use the N line, the neutral line?
No, sometimes we may not also have neutral lines. That is also
In unbalanced systems.
even in unbalanced system, we may have, it is possible to have unbalanced 3-phase, 3-wire system without neutral line. It's possible. Okay, but normally, more often we will have the neutral line.
Sir, but then KCL would not be.
No,
there would be
KCL is
some
always true. KCL is always true. Okay, so definitely if the neutral line is not there, then your IA plus IB plus IC must be equal to 0. That will happen. Okay.
Yes, sir, okay.
Then you can say that, okay, then IA, IB and IC will not be of equal magnitude. That's true. If ZA, ZB, ZC are not equal. Acha, okay, so let me come to, so power measure, 3-phase power measurement. Okay, so in our last class, we were talking about wattmeters and how to connect wattmeters. Okay, so let me just copy this. Let me make it a bit cleaner. Okay. Now we want to measure the total power consumed by these three loads. How to connect wattmeters? Okay. So suppose we have 3 wattmeters. Each one will be used to measure the power consumed in ZA, ZB and ZC respectively. How to connect? Okay, so let me see how much you remember. How many coils or how many terminals does a wattmeter have?
Four.
Yes. It has 2 coils or 4 terminals, one coil for measuring the current, which we call current coil, another for measuring the potential difference, which we call pressure coil or PC. Okay, suppose, and there this is plus, this is minus, this side is plus, this side is minus. We want to measure power consumed in ZA. So we have to measure current flowing through ZA and voltage across ZA. Okay, so for your ease, let me just give some names to these 2 points, like what can I call? Okay, let me use just numbers 1, 2, 3, 4, 5, 6. Okay, so these nodes I will denote by numbers. 5, node 6, okay, etc. If you need more, 7, 8. Okay, tell me how to connect this wattmeter to measure power consumed by ZA.
So current coil will be in 7 and 8 in series, and
Yes.
3 and 4 will be 5 and 6 with parallel.
Yes, absolutely right. So we may just put this current coil in series with the ZA, so that the current coil is now measuring the current flowing through ZA. Okay, now we have to measure also the voltage across ZA. To measure voltage across ZA, let me connect terminal 4 here, 4 with 6, and 3. Where can I connect? 3 should go to
5.
5. Yes, absolutely right. But any other option?
7.
7. 5 and 7 are same. Why it's same? Because there is no voltage drop across this current coil. Current coil impedance is 0. So you can connect it to 5 or to 7, same. It is easier to connect to 7 because otherwise the diagram will be a bit uglier. Okay, so similarly, now one more wattmeter I am going to connect. Tell me how to do that. Okay, so current coil, pressure coil, okay, plus minus, CC, PC, okay. Let me give names. 11, 12, 13, 14, okay, this is 15, this is 16, okay, then 16 and 6 they are same, so let me give you, then maybe this is 17, what else, maybe something here, 18, 19, 20, 21. Now, the purpose of this wattmeter is to measure power consumed by ZB. How should I connect? Please go ahead. Tell me. To measure power in ZB.
13 and 14 in series with 18 and
Okay.
19.
So 13 and 14 goes in series with this line. Okay, so that it measures like this. Okay, now, so the wattmeter is measuring the current, how to get the voltage?
Sir, 11 with
12,
18 and 12 will be in
11, yeah, so
6.
12 we can connect to 6, okay, minus side to the minus side, uh, and 11 I can either connect to 18 or this is what, okay, 18 or 15 same, so I can connect it here. Okay, in the same way, now to get the power in load C, let me do it for you. Current coil, pressure coil, plus minus, say plus minus. Okay, so I will put this in series here, and the voltage coil should be maybe like this, and this has to cross, no way, here. Fine? Any questions so far?
No, sir.
Okay, so
the
now,
terminal 12 will be negative. You write it positive.
please repeat.
Terminal 12, sir.
Terminal 12 here.
It will be
Oh, yeah,
negative.
yeah,
You
yeah.
write
Thank you, thank you,
positive.
thank you, thank you. This is, yeah, thank you. Any other mistake? No, fine. Yeah. Thank you, yeah. Acha, now, so we see that for a three-phase load, we need 3 wattmeters. But now we will learn a special trick called 2 wattmeter method, so that with 2 wattmeters we can measure the total power. Okay, I will tell you the method and then I will justify. Okay, let me clean it up. Okay, so for this method to work, one condition is necessary. That condition is that the sum of the 3 line currents should be equal to 0. Okay, so I remove the neutral. Okay, so it is necessary that sum of 3 line currents must be equal to 0, otherwise this method will not work. Now listen very carefully how I am going to connect the 2 wattmeters. Okay, so first let me draw 2 wattmeters. Okay, and they will have 2 coils each. Current coil, voltage coil, okay, suppose plus, minus, plus, minus, plus, minus, plus, minus. Now, the rule is this: put the current coils in any 2 line, any 2 line you like. Which 2 lines you like? Tell me, any 2 lines. Okay, so for example, let me choose, I mean here this line, because here it's easier to draw. So let me put this current coil here. So put the current coils in any 2 line, whichever you like. Now this current coil, where would you like to put it? in line B or in line A? You can choose. So let me choose line A. Once that is done, next, the voltage coils should measure the voltage of the selected lines with respect to the unused unselected line. So here we have selected line A, so I will measure the voltage of line A with respect to the unused line, unselected line, that is line B. Similarly, now where should this voltage coil go? It should measure the voltage of line C with respect to the unused one, line B. That's the rule. Put the current coils in any two line, whichever you like, and the voltage coils should measure the voltage of the selected lines with respect to the unselected line. Is the rule clear?
Yes, sir.
Okay. Now,
So can you repeat the rule? I had some internet problems, so I didn't hear.
okay, I repeat. So take 2 wattmeters and then put the current coils in any two line out of the 3 lines, whichever you like. Okay, we have 3 lines, 2 current coils, so put those in series with any 2 lines you like. And then put the voltage coils such that they measure the voltage of the selected line with respect to the unselected line. So here this wattmeter is chosen to measure current of line A. So I have put the pressure coil of this wattmeter between line A and the unused line, that is line B. Okay. Similarly, this wattmeter, call it W2 and W1. Okay. So this is CC, this is CC, this is PC. Okay. So I have chosen to put current coil in series with line C. So this is C, B and A. Okay. So therefore, the voltage of voltage coil of wattmeter 2 is measuring the voltage of line C with respect to the unused line, that is line B. Is it fine now? Okay, fine. Next, what will be the total power? The total power, total 3-phase power will be just the sum of W1 plus W2. Only 2 wattmeters, only 2 readings we have. Just add these 2 readings, that will be the total power. We don't need 3 wattmeters. How is that possible? So that's what I am going to justify now. Okay, so suppose I call this current as IA, IB and IC. They are all functions of times. And suppose this voltage is VA plus minus from here to here, then VB plus minus, okay, and VC plus minus, like this. These are all functions of time. Now, consider W1. Instantaneous power sensed by W1 at any particular moment is how much? At any particular moment, how much power is sensed by W1 in terms of these currents and voltages? I can also call, say, VAB is like this from line A to line B, that is VAB. and so on. Okay. So how much is the
VAB into I80.
yes, yes,
I80 into VAB.
IA into VAB. Okay, let me not write T all the time to make it cleaner. So that is W1. Acha. Then how much is the power, instantaneous power at any particular time? Okay, so I can write T here, instantaneous power. I'm not writing time all the time. Okay, so how much is the instantaneous power sensed by W2? IC V
to VBC.
BC, or better to call it CB, C minus B. Okay, so VCB is from here to here, plus downside minus above. Okay, so how much is W1 plus W2? IA VAB plus IC VCB. Now how much is VAB? VAB is in terms of the phase voltages, in terms of VA, VB, VC, what can we say?
VB minus VA.
VB minus VA. Little bit correction required. VA minus VB. Please check the direction. Okay, so for VAB, positive end is towards A. Okay, also for VA, positive end is towards A. But for VB, the positive end is, not towards A. Okay, so this is VAB. Please check. Is it correct? Then plus IC, what is VCB? VC minus VB.
VC minus.
Yes, right. So now I can write it as IA, VA, just expanding these products. So IA, VA, I will also have IC, VC, and then I have VB twice. So let me write VB common minus, and I have IA plus
IC.
Yes. Now, what is this last term? IA, VA plus
Minus IC.
Absolutely right. Okay. So this I can write as VB into minus IB. Because, why? Because IA plus IB plus IC is equal to 0. That's what we need. We started with that assumption. The sum of the three line currents should be 0. So then what is this? W1 plus W2. IA, VA, IC, VC plus IB, VB. This is total power at any particular moment, right? So that means the instantaneous power sensed by W1 and W2 together is same as the total instantaneous power at any moment. However, these wattmeters will not give you instantaneous power. Wattmeters gives average power over time. Okay, so therefore, so we can also write time average. So let me write reading of wattmeter 1 plus the reading or output of wattmeter 2. Okay, so that will be what? That will be basically time average of W1 plus W2. But since W1 plus W2 at any moment is the instantaneous power consumed by the three loads together, so what will be the time average of W1 plus W2? So that will be average power, average total power, or I write total average power of the three-phase load. Okay, so this is why this method works. Only with 2 watt meters we can measure total power. Now tell me, will this method work for balanced loading? Yes, no? Will this method work for balanced load? What do you think?
Yes.
Yes. Will it work
Yes,
for...
sir, it might.
Yes? Acha. Will it work for unbalanced loading? What is the difference between balanced loading and unbalanced loading? In balanced loading, ZA, ZB, ZC are equal. For unbalanced,
Equal.
yeah, and for unbalanced loading, they may not be equal. Will it work for unbalanced loading?
Yes,
No,
sir, it
sir.
will work.
Acha. Okay. Will it work if this neutral line is present?
Yes, sir, it
Yes,
will work.
sir.
Will it work if the neutral line is present and the load is balanced?
Yes, sir.
Will it work?
Yes.
Will it work if the neutral line is present and the load is not balanced?
Yes, sir.
Yes, sir, it will
Yes.
work.
Acha, will the sum of IA, IB and IC be equal to 0 if the neutral line is present and ZA not equal to ZB not equal to ZC?
Yes.
How?
No, sir.
No, sir. No, sir.
Okay, so if, see, if
Yes,
this,
sir. Yes. They will
see, if
have to
this
be
neutral
balanced.
line is not present, then IA plus IB plus IC must be equal to 0. Okay, here we have IA, here we have IB, and here we have IC. They come and meet at this point, and then there is no point, no other path for this current to go, so they must add up to 0. No matter whether ZA, ZB, ZC are equal or not. Kirchhoff's current law must be valid. Okay, but if there is one more path for the current to flow, I mean that means the neutral line is present. If this neutral line is present, then IA, IB plus IC need not be equal to 0 always. Because if they are not summing up to 0, the residual current will flow through the neutral. Right? No problem. But if ZA, ZB, ZC are equal, then they will be anyway equal to 0. I mean, they will sum up to 0. Okay. So, and when will this method work? This method works when the sum of the three currents is 0. If the neutral line is not present, then the sum must be 0, so it will work. If the neutral line is present and the load is balanced, then also the sum will be 0, then this method will work. But if the neutral line is present and load is not balanced, then the sum of the three currents will not be equal to 0, and then this method will not work. Okay, because we have assumed IA plus IB plus IC equal to 0. Okay, so any questions so far?
Sir, is there a case where the neutral line is not present but the load is not balanced?
Yes, why not? It's possible.
So, will it work?
Then this method will not work, No, it will work because you stated that neutral absent and load unbalanced, right?
Yes, sir.
Okay, but now you tell me how much is IA plus IB plus IC?
0.
0.
0.
So
0.
this method will work.
Okay, sir.
Okay, so 2 watt meter works. Fine. Achha. Now I will just give you one homework. Okay. Suppose we have 3 sources balanced. VA is like this, plus minus, VB plus minus, and VC plus minus. So balanced load you consider. So this is Z angle theta, this is also Z angle theta, this is also Z angle theta. Okay, acha. Now I also tell you that VA is equal to, so VA is actually from here to here, okay, and similarly VB and VC. So VA is say V naught sine omega t, VB is V naught sine omega t minus 120 degree, and VC is V naught sine omega t minus or plus 120 degree. Achha. This current is IA, IB and IC. Tell me how much is the value of IA. So achha, before that, tell me what is the phasor value of VA. How do we represent it?
P naught upon root 2 angle 0.
Absolutely right. Similarly, VB.
V naught by root 2 angle.
P naught upon root 2 angle 120 minus 120.
Absolutely, yeah, minus 120, and VC is same magnitude
P naught
but plus
plus
120. Achha. Now, then you tell me how much will be these currents. First, how much is IA as phasor?
V naught by Z root 2 angle minus
Z.
theta.
So let me first write VA by root 2, VA by Z angle minus theta, which you can also write as V
upon
naught
root
by,
2.
absolutely.
Sir, upon root 2.
Okay, similarly, IB will be I missed Z root 2 angle minus 120 minus theta, and IC will be V naught by Z root 2 angle plus 120 minus theta. So now you tell me the functional form of these currents. IA will be
Root 2 sine omega t minus theta. Sorry, V naught by Z sin omega t minus theta.
Sin omega t minus theta. IB will be V naught by Z sin omega t minus theta minus 120 degree, and IC will be V naught by Z sin omega t plus 120 minus theta. Acha. Now tell me how much is the total load power, total active load power, say, I mean actual average power. Consider one load at a time. First this load, how much is the power consumed by this? VRMS, IRMS cos theta. How much is VRMS?
V naught
V naught
upon
by root
root
2.
2.
Okay, so
V naught into I naught upon.
yeah, so V naught by root 2 is VRMS. How much is IRMS, current RMS?
V naught upon Z upon
V
root
naught
2.
by Z root 2. How much is the angle between the voltage and current?
Theta, cos
So cos
theta.
theta. So this is by one, this is the power consumed by one load. So how much is the total power, total active power, average power consumed by the three loads?
Into 3.
Into 3.
Into 3.
Okay, so that is basically 3 V naught square by 2 Z cos theta. Achha. Now consider instantaneous power. Instantaneous load power, total load power. How much is that? So that will be
VA into IA
yes,
plus
VA
PV into IB
VB into
plus VC
IB
into
plus
IC.
VC into IC. Now you know the expression of VA, VB, VC, IA, IB, IC. Okay, all are given here. Okay, so you multiply them and add them and do some trigonometric simplification, okay, which will take maybe a half a page of calculation, and find out. So these are all functions of times. Okay, these are all functions of VCT, ICT, and so on. So all are, so this is a function of time. But to multiply and add them, what you will get is this. Constant, not a function of time. Okay, so this is actually another advantage of three-phase.
It will be average. No?
Yes, yes. Please repeat.
Sir, it will be average. No? Is it instantaneous power total?
No, no, no. See, this is what? This is the total power consumed by, total power consumed by the three loads on an average. Okay, so basically time average. Because VRMS, IRMS cos theta, that is the expression of average power.
Average power.
Right. So we have already calculated the average power. But now here we are calculating the instantaneous power without doing any average. Don't do any average. Okay, so no need to do any average. But without doing any average also, you will see that the total comes out to be same as the average power. You don't have to do the averaging. Okay, so so you'll see that total power, total instantaneous power is same as the average power. So overall, the power flowing from generators to the load side is not fluctuating in nature. Okay, it is constant. This is one advantage. So, of course, assuming balanced loading, if it is not balanced, then it will not happen. But assuming balanced loading, we see power flowing from load to source to load, total power, three-phase power is actually constant. Okay. So this I leave it as a homework to complete these steps. Simple trigonometric for simplification, nothing else. Okay. Achha, fine. This is almost the time before taking up another topic. Let me see whether we can solve some small problems, because time is almost up. Okay, so let's solve some small problem. At least one problem. Okay, so we have a three-phase supply, V1, V2, V3, and they are of magnitude 100 volt each, RMS value, 120-degree phase difference between among them. And we have three loads, one capacitor, one inductor, and one short circuit connected like this. Let me check your how much I am able to convey you today. So what kind of connection is it? Star connection or delta connection?
Star connection.
Star connection. Both load side and source side, both are in star. Achha, is it a balanced system?
No, sir.
Achha,
No, sir.
is the supply balanced?
Yes, sir.
Right. Is the
Yes, sir.
load balanced?
No, sir.
No.
No. Supply is balanced, load is not balanced. So overall, this is not a balanced system. Okay, so we cannot utilize the symmetry of the circuit to solve it easily. So we have to solve it in a normal manner. I mean, okay. Achha, fine. So what do we have to find out? We have to find the current I, phasor value of this current I in the third line. Achha, so is there any earth point, ground point? No. But anyway, we can take any point as the reference point. Any one point can be taken as the reference. So this is grounded, 0. So this point is 100 angle 0 degree. This voltage. V2 is 100 angle minus 120 degree. And here we have 100 angle plus 120 degree. Let me call this current as I1, okay, this as I2, and this is I. How much is I1? Anyone?
V1 by minus J.
V1 by minus J. No, not right.
V1 minus
We
y,
should-
V1 minus y, V3 by.
Absolutely right.
We should
Yeah.
take
Yeah,
a
so
volt.
this point is at V3, since this is short circuited, so this is also V3. Okay, so this is also 100 angle 120 degree. Okay, so if so, then I1 is V1 phasor minus V3 divided by minus J. Okay, so this is 100 angle 0 degree minus 100 angle 120 degree divided by J. Okay, acha. How much is I2? I2 is V2 minus V3
V3
divided
upon
by plus J.
J.
Okay, so that is, let me not, so V2 minus V3 by J. Achha, then finally, how much is I? Phasor value will be
I1 plus I2.
I1 plus I2.
Minus I1 plus
Minus I, absolutely. Okay, minus
Yeah.
I1 plus I2. Now we have to solve it. So let us use phasor diagram. So suppose this is V1, this is V2, and this is V3. Okay, to get I1, I have to subtract 3 from 1. Okay, so 3 from 1 is this one. Okay, and the length of this phase voltages are all 100 volt each. So how much is this voltage, this red voltage? We have studied today
100 root 3.
100 root 3. What is the phase angle of this voltage? How much is this angle?
30 degree. 30 degree.
Minus 30 degrees. Okay, because this is downwards, minus 30 degree. So this is 1 minus 3. Achha. Then we have to also calculate V2 minus V3. Okay, V2 minus V3, that will be this one. How much is this voltage in phasor form? Magnitude
100 root 3
100
minus
root 3 angle
Minus 90.
90 degree. Okay, fine. Acha. So current I will be therefore this voltage 100 root 3 angle minus 30 degree divided by minus J. Okay, divided by minus J means angle will become
Multiplied by J.
multiplied by J,
Plus
so angle
90.
becomes
Plus 90.
plus 90 degree. Acha. And then another term is 100 root 3 angle minus 90 degree. But then we have to divide by J. Divide by J means angle will become
Minus 90.
minus 90 degree. Okay. This is the sum of I1 plus I2, but we have to also put this minus sign from here. Okay, now you can use even a calculator to solve it. But anyway, don't use the calculator. Let us do it on pen and paper. So can you tell me how to simplify this? So let me write this as 100 root 3 common. Okay, then we have 60 degree.
60 degree.
So one angle 60 degree. One angle 60 degree minus. Achha, let me put this minus outside. That's easier. Correct? Yeah. So one angle 60 degree, and this is minus
1 and 2
plus
minus 180.
180 degree. What will be the sum? Okay, so one vector is at 60 degree, another is at, oh, I have a minus sign here. Please check. This is minus 180 degree. Okay, where will be the resultant?
Root 3.
The resultant will be here. Yeah, so it will be exactly halfway between. Okay, so this angle is 60 degree. So this will be
60.
60 plus 60, 120. Right? And how much will be the length?
Root 3 times.
Root 3 times? No. I mean, if this length is 1, if I consider this length to be 1, then how much is the projection here?
It will also 1, sir.
It is cos 60 degree, right? This is cosine 60 degree. Am I correct? So 2 times cosine 60.
1.
So that will be 1. So that will be 1 angle 120 degree. Okay, and here outside we have minus 100 root 3. Okay, so finally this is what? Because of this minus sign, you can add add or subtract 180 degree inside. Okay, or you can also keep it like this. So this is the answer. You may also write 100 root 3 if I minus 60 degree. That is also possible. Okay, that's the answer. So let me stop at this point. Tell me if there is any question.